This video lecture covers thermal energy and concepts related to heat. The corresponding lesson was created by Derek Spencer from material made by Ebenezer Luma. This video was made possible through the NSF-funded Boat of Knowledge in the Science Classroom projects at Ohio University. What is the difference between heat and temperature? You may already understand this without even realizing it. Here's a bit of a thought experiment which may help you to understand it on a higher level. Say we take two containers filled with water at room temperature, a small drinking cup, and a gallon jug. If you were to heat both of those on a stovetop for the same amount of time and on the same heat setting, and then take temperature readings, which container would have a higher temperature? Obviously the small cup, right? Say after you've heated both containers, you poured the hot contents of the drinking cup into a new gallon jug and topped it off with room temperature water. Do you think the temperature of this new jug would be higher or lower than the gallon that you heated directly? Under ideal conditions, both of these jugs should be the same temperature. In the previous scenario, an equivalent amount of heat was applied to both of the containers using a stovetop. But because the smaller drinking cup held less water, that heat was more confined, and we could say it had a higher temperature. Temperature, then, is a measure of the average heat of a substance and is typically reported in degrees Fahrenheit, Celsius, or Kelvin. Heat is the total internal energy of a substance due to movement and interactions at the molecular level. It's helpful to imagine an object being composed of a bunch of small vibrating molecules. The hotter the object is, the more the molecules vibrate and interact with other molecules. It is important to realize that just because something is cold, it does not mean that it has no heat. An object or substance feels cold to us because the heat energy produced by your body is being transferred to the colder object. If you were to touch a cold object, heat would be transferred to that object until it reached the same temperature as your hand. Under normal circumstances, heat energy typically transfers from a state of high energy to a state of low energy. Between two objects or substances, this means energy will flow from the warmer substance to the cooler one until a thermal equilibrium is established. There are three main types of heat energy transfer: convection, conduction, and radiation. We will go over each one of these heat transfer concepts in detail in the following slides. First, convection. Convection is a primary mechanism involved in energy transfer within liquids and gases. In convective heat transfer, a warmer liquid or gas rises while a cooler one sinks. For instance, when heat is applied to a given amount of air or water, the molecules of that air or water become more excited and spread out. The fluid becomes momentarily less dense and rises. Upon cooling, the fluid becomes more dense and sinks. This generates a mass movement of the substance, similar to the pictures on the bottom of the screen. How does a hot air balloon work? Pause the video here and take a few minutes to come up with an explanation before continuing on. The air inside of the balloon is heated with a propane burner. Hot air rises and fills the balloon, while cold air is dispelled. The density of the air in the balloon becomes less than that of the surrounding air, and it floats due to a buoyant force. This is similar to releasing a helium balloon or putting ice cubes in water, except the buoyant force in this case is created by convection. When it's time for the pilot to descend, hot air is released through vents, allowing cold air to displace the hot air. Convective heat transfer is responsible for the generation of many Earth systems. Ocean currents are driven by water density differences due to temperature variation between locations. Large and small-scale wind patterns are dominated by differences in temperature, and the Earth's tectonic plates are driven by differences in temperature between the mantle and core. The second mode of heat transfer is conduction. Conductive heat transfer occurs through the collision of atoms or molecules in close proximity. A conductor is a material which is easily able to transfer heat through these interactions. Can you think of materials which exhibit good conductive properties? If you were cooking spaghetti on the stovetop, would you rather use a metal or wooden spoon? You'd use a wooden spoon to prevent burning yourself on the conductive metal spoon. When you heat one end of a good conductor, heat is transferred from the hotter end to the cooler end. Solids generally make good conductors because of how close atomic bonds are in relation to one another. Upon heating of a good conductor, the free electrons present in the conductor become excited and are easily able to transfer energy between atoms or molecules through collisions between these atoms and molecules. This continuous process is what makes metallic objects good thermal conductors. Metals like copper make excellent heat conductors. Nonmetals may be good or bad conductors depending on molecular structure and electron configuration. For instance, plastics are typically poor conductors. Liquids and gases are very poor conductors. Materials which are poor conductors are called insulators and can be used to retain heat. If you're an avid coffee drinker, you'd want to drink it out of a styrofoam cup rather than a metal or glass cup. The final mode of heat transfer is radiation. When energy from the sun travels to Earth and heats it up, the energy is said to be radiating. But how is this any different than convection or conduction? Pause the video here and try to come up with an explanation before moving on. Radiation is different from convection and conduction because it does not require molecular interactions to exchange energy. Electromagnetic waves radiated from our sun travel through the vacuum of space without colliding with any particles. Once these electromagnetic waves reach the Earth's atmosphere, gases in the atmosphere absorb the radiative heat and warm the Earth's surface. Why does it take so long for water to boil? Can you think of other liquids which boil faster? The ability of a substance to retain heat is known as heat capacity. In a technical sense, the heat capacity is the amount of heat required to raise the temperature of a given mass of substance by 1 degree Celsius. Substances with a large heat capacity are able to retain more heat, and substances with a small heat capacity are not. Water is a unique substance on Earth because it is naturally present in 3 phases, as ice, water, and vapor. Under standard Earth conditions, water has a high heat capacity, and because of this, water is the most commonly used coolant. The only caveat in using water as a coolant is that it is not able to cool substances below 0 degrees Celsius without the help of antifreeze, or it will end up freezing and possibly destroying coolant lines. A useful equation for heat capacity is Q equals C times M times delta T, where Q is the amount of heat applied to the substance in joules, C is the heat capacity proportionality constant expressed in joules per gram degrees Celsius, delta T is the observed change in temperature of the substance, and M is the total amount of substance being heated. Using this equation, we are able to measure how much heat a given material will be able to retain, or how much heat is needed to raise its temperature by a certain amount. Given any 3 of these variables, we can find the variable of interest using this equation. Take out a piece of scratch paper and try to solve the following heat capacity problem. Pause the video and resume once you've come up with an answer. We can first find the total mass of water being heated using the relationship between density and volume. If we started with 50 milliliters of water and the density of water is 1 gram per milliliter, multiplying will give us a total mass of 50 grams of water. Since we are heating the water from 25 to 75 degrees Celsius, the corresponding change in temperature is the difference between the final and initial temperatures of the water. Subtracting, we get a 50 degrees Celsius increase in the temperature of water. Finally, we can plug all the variables into the equation to find the total heat necessary to warm the water to this final temperature. Multiplying, we get 10,450 joules, or 10.45 kilojoules, heat needed as input. Heat capacity is valid for a pure phase substance not undergoing any phase changes. For the previous example, we only looked at pure water undergoing a temperature change. The heat capacity equation is valid from 0 degrees to 100 degrees Celsius. Ice and steam have their own heat capacities, but as you can see from the above, ice water and water-steam mixtures rely on a different principle called latent heat. The heat capacity equation from before is essentially a linear equation where temperature is the y-axis, heat is the x-axis, and the slope of the line is equal to the heat capacity constant. Different from heat capacity, Latent heat is the amount of energy required to change a given amount of substance from one phase to another. Put another way, this is the hidden heat inherent during a phase change. In a phase change, the temperature of the substance remains constant until all of the substance has changed phases. What would happen if you stuck a thermometer into a pot of boiling water? The heat source is still providing heat energy, but the temperature of the water remains the same at 100 degrees Celsius. You can see water vapor leaving the pot. This vapor will be hotter than the boiling water until it loses enough energy to recondense into water. The same thing happens when you leave a pool. You feel colder than you normally would because water is evaporating off of your body and pulling the heat from your body. This cold feeling is due to latent heat. The equation for latent heat is simply Q equals M times L, where Q and M are defined as previously for heat capacity, and L is the latent heat proportionality constant expressed in joules per gram. Depending on the phase change, there will be one of two latent heat values: the latent heat of fusion and the latent heat of vaporization. For water, latent heat of fusion describes freezing or melting, and latent heat of vaporization describes evaporation or condensation. Using your scratch paper, try solving the following latent heat problem. Pause the video and resume once you've come up with an answer. First, we must select the proper latent heat constant. In this case, water is freezing, so we use the latent heat of fusion. Note that the latent heat of fusion is greater than the latent heat of vaporization. This means less energy is released when water freezes than is gained when water boils. Now we can easily calculate the heat loss required for this phase change to occur by multiplying M and L. We need to remove 16,700 joules, or 16.7 kilojoules of heat, to freeze 50 grams of water at 0 degrees Celsius. Note that this equation only works for water at 0 degrees Celsius. If we wanted to calculate the amount of heat required to freeze water initially at 25 degrees Celsius, we would first need to use the heat capacity equation to find out how much energy needs to be removed from the water to reach 0 degrees Celsius. Then we would add this to the amount calculated here.